Alright, here we are again for lesson 39 of CENG 3306 Mechanics of Materials. Alright, this will have a short bit of notes today that I want to get through for this last portion. I do have a lesson 40 that I wish to cover, that I wish to record, and I'll either record that later today or possibly tomorrow, and I'll get that posted fairly shortly. But this will be the last lecture for inside the class, for an in-person recording session. Okay, so let us finish this. So we are in sections 13.2 and 13.3 of the Euler text, and let me make sure, yep, we're good. We are in 13.2 and 13.3 of the Euler text. Our objective here is, I'm just going to work through a simple example, just one more example is all I want to do here, of designing a column using the Euler buckling equation. So, I want to design a column using the Euler buckling equation, and I am going to remember that P critical is equal to pi squared EI over KL squared. And we have the following support conditions: pin-pin, fixed pin, fix-free, fix, and the bizarre flagpole fix-free. Fix-free. Alright, and then I will say for each of these, k equals 1.0, k equals 0.7, k equals 0.5, and k equals 2.0 here. And so I'm just going to work through one example here. And let's say I'm given a whole bunch of information about a column. I'm going to select the most economical wide flange section. So say L equals 20 feet, sigma y is going to be 36 KSI, P equals 125 kips, factor of safety for buckling is 2.0. So I'm actually going to use a higher factor of safety for buckling than I will yielding, because as we've discussed, it's a much more critical, much more catastrophic failure mode, 1.5, and pin-pin. If we have pin-pin, we know that k, so we have k, I'm telling you that it's pin-pin, and for this we know that the k is equal to 1.0. And I want to find most economical W section. Alright, so I am going to assume buckling controls. That's usually a safe assumption, but we would have to go back and check. So when designing, I'm going to assume that buckling controls, and then I'm just going to go back check for yielding. My goodness. Assume buckling controls. And so then, we will know that actual is less than or equal to allowable. We always come back to that. Allowable. And then, so we are saying that 125 kips equals the actual load, P actual, the actual axial load, less than or equal to P allowable over the factor of safety, which is equal to pi squared times 29,000 KSI times, you know what, here's the issue though. I need to, if I'm going to look at steel tables, I need to know whether I should look at the IY or the IX. I need to actually look at one number. I'm going to look at the IY. typically because this is defined as weak axis bending. Generally, for W sections, in almost all cases, your IY is going to be less than the IX. So I'm going to use the IYY over 2.0 times 1.0 times 20 feet times a conversion of 12 inches per foot. Oh, and this, of course, squared. Doing this, we will find that IYY, or the just IY if you want to think of it that way, 50.3 inches to the fourth power here. And notice, IYY, it's a fun thing, that's a fun word to say, IYY. Yes, I am still 5 years old, why do you ask? IYY is less than IXX for W sections. There may be some weird outlier that I'm not aware of, but generally it's much less for, generally the IY is much less than the IX, unless there's some weird outlier. So min of IX, IY equals IYY. Okay. So, looking at this, looking through the table, I will find, again, the way I do this is I look at the table and I find a series of, I look at this series of shapes, and within each one, within each family, like the 8, the 10, the 12, etc., I find the lightest one that will have the required IYY. So let's look at this, and I can just tell you some sections. I got these from the steel table. W8 by 48. Each of these is going to have sufficient IYY. This is 50.9. That was the lightest W8 by 48 that would work. W10 by 45. This was 53.4. The lightest. This is the lightest one. 53.4. So I'm just looking for ones that have an IYY greater than 50.3. The W12 by 50. IYY is 56.3. And the lightest W14 by 53 was 57.7. And look, this one is going to control. The W10 by 45 is going to control. It's the lightest. It only weighs 45 pounds per foot compared to 48 here. So even though this has a higher, well, never mind. There is one other that I might consider. The only one I might consider besides that is this one. This one has less depth, so maybe that would be beneficial. So if you maybe, or maybe if this one had, maybe if this one had a really narrow flange, maybe you'd be better off using this one. It just depends on, there are certain cases if you're trying to say conceal a beam within a wall, it's beneficial to have one dimension minimized over another, but if we're keeping it simple and just saying the lightest one wins, this one's going to control. So I am going to say I'm going to recommend use W10 by 45. And then, remember I assumed that buckling controls, but I need to actually be sure. So I'm going to check a W10 by 45 for crushing or yielding. And I know from the table that the cross-sectional area of this is 13.3 inches squared. And then moving along, I can just work through the same equation as before. 125 kips over 13.3 inches squared equals sigma actual is less than or equal to sigma y, the yield stress, over the factor of safety for yielding. Notice, remember, I'm using different factors of safety here for yielding and buckling, which is going to be equal to 36 KSI over 1.5. So then 9.39 KSI, or KSI, Gibbs per square inch, is less than 24 KSI. Oh my goodness. 24 KSI. So we know this thing is okay for crushing. So okay will not crush or yield. And that'll do it for this lesson. Again, I mentioned this was going to be really short. I just had one quick example I wanted to work through. I will have a lesson 40 that I'll probably record later this afternoon and post for probably before 5. Okay, that'll do it. And as always, thank you.